Hi, today I'll be talking about the Universal Turing Machine as a part of the extra credit opportunity for theory of computing. I ended up choosing this topic because it was something very interesting to me that there is a universal machine that can read input and take in other Turing machines as that input and perform computation on them. And it was great doing the research for this presentation and learning more about it. I wish we had touched a bit more on it in class to truly understand how this is really the baseline of computers and technology today, especially software and hardware. So let's start with a little introduction of what is a universal Turing machine, and quite simply, it is a Turing machine as we know it. The universal part means that it can simulate an arbitrary Turing machine with an arbitrary input and alphabet and compute as if that one does. And so this idea came about by Alan Turing in his 1936 paper, where he says, "It is possible to invent a single machine which can be used to compute any computable sequence. If this machine U is supplied with a tape on the beginning of which is written the SD of some computing machine M, then U will compute the same sequence as M." So what he's basically saying is the universal Turing machine does exist, which you can invent to take in an input of a Turing machine M and decode that machine, the standard description of an action table, and use its input, and then U will compute the same sequence M does. So before we see a formal definition of this, I'd like to go over a little bit of format and notation purposes for Turing machines. So the input to a Turing machine is always a string. However, Turing machines themselves are not strings, and that is a part of the input to a universal Turing machine. So to provide an object or a Turing machine as the input, we must encode it as a string. And so, because Turing machines are objects in and of themselves, they can be inputs to other Turing machines. We just need to encode it as a string. So for our purposes, we will use the angled brackets. And so our notation for the encoding of an object O into its representation as a string is O between the angled brackets. So then, likewise, you can think of O is going to be our Turing machine M, and we can encode it with those angled brackets to be the input of our universal Turing machine. However, our universal Turing machine will also need to take in the input string to the Turing machine M. So if we do have several objects or strings, we denote their encoding into a single string, as you can see with O1, O2, all the way up to OK, where K is an arbitrary integer. So then the universal Turing machine can decode this input and interpret it properly. So now we will take a look at formally what the universal Turing machine is. Formally, we define it as U, which is equal to on input M and W, where M is a Turing machine and W is a string. It simulates M on the input W, and if M ever enters its accept state, U will accept. If M ever enters its reject state, U will reject. So now that we've seen that we can encode Turing machines as strings and pass in their input together, U will take in this input and decode the machine M and the input W, and then compute that output. So here's a little graphic of how that can be done. As you can see, the first part of the tape is the decoding of the machine M, followed by the input to M, which in our case would be the string W. And then after that will be the output of U. And so this is kind of like the action table, the standard description of the action table that Alan Turing talked about in his paper. So what's the relevance of this universal Turing machine? Why are we talking about it? Well, first, it's important to note that the universal Turing machine is a recognizer and not a decider. And this became important in the halting problem, where we see that ATM is undecidable. However, it is recognizable. It's recognizable by the universal Turing machine. It's a better way to think about it is that the universal Turing machine is an interpreter of Turing machines. An analogy that can be made is that the universal Turing machine interprets Turing machines as if they were computer programs, just like how a C interpreter can interpret programs written in C. So this ultimately led to the idea of the stored program computer and von Neumann architecture, where the program data and memory are stored together. And this introduced a new world of computers where before this idea, computers were built with one specific purpose in mind and for one specific task. And the program data was not stored in the computer. A lot of times, the computer would either just do that task and that was it, single issue, or you would put in a punch card and the computer would perform the task and then it would be done. However, this new idea stores the program data and the instruction in the same memory space, which ultimately leads to this general purpose computer, where we can recursively run software on top of software on top of software, which follows the idea of the universal Turing machine, which can run and compute and simulate a Turing machine, which then could also simulate another Turing machine, and recursively this builds up and up. This is really important in today's world as we're in 2021 and we're implementing further hardware and further software. I'm currently running Linux, and I could get a virtual machine that could then run software that could just run another program on top of that. And this all kind of comes from this general purpose idea of the universal Turing machine, where I'm running hardware that is running software that is running further software to run more hardware to run more software. And it all kind of comes from this idea from Alan Turing in 1936, which led to the stored program computer, and now we have general purpose machines, which are our laptops sitting in front of us right now, where the interpreters can take in a software program and simulate it and run it. We don't have a single purpose machine. I can do so many things on my computer as you can as well. I'm not limited to just punching in a specific input and receiving that output. So that's just all I kind of wanted to talk about. It is a really interesting topic and area of study. You can see some of my citations go a little bit further in detail, but I thank you for listening to my talk and hope you learned something.